Welcome back to part 15, the final part of Password Cracking 101 plus 1. In the last video we looked at moving away from Hashcat and introduced MDX-find, which is fantastic for attacking both large hash sets and lots of unknown hashes. So we gave MDX-find a file containing 5 unknown hashes, and we were able to work out and identify that 4 of them were cracked here with their hashing algorithms that MDX-find found for us, and there was also a final elusive hash that you can have some fun with if you want to test with MDX-find further. For the last part, we are going to look at some attack analysis, and we're going to use the PAC toolkit for this. Now, PAC was developed by iFelix, whose GitHub is still available, and you can grab this. However, one of the Python files inside of this suite of tools, I believe, had an issue with an outdated Python dependency or a package that was hard to sort of get availability for now. So, Hydrace has got a fork of this, which gets around that, and you might find it gives you slightly better support. However, they both do exactly the same thing. There is a blog here written by iFelix which goes into a bit more detail than the GitHub provides about how to use PAC for things like pattern detection, mask detection and things like that. And HopCH has also tried to enhance PAC in Rust, although the last time I did look at this it wasn't fully complete yet, so watch this space. The first of the 4 tools in PAC is Statsgen, and this provides us some 101 stats about our cracking sessions. You can feed Statsgen a pot file is a good example after you've conducted an audit or whatever you might be doing, and this will spit out some information about what you've been doing. As you can see here on the right, it will look through your pot file and sort your cracked passwords in terms of length. So the most popular password was 8 characters in length, or the most frequent I should say, and then 9, 6, so on and so forth, depending on how big your pot file is and what it's got inside. It'll also sort out via character set and mask. So in this example, 44% of the identified cracked passwords used a string digit mask. So it gives some great insight into how passwords are being chosen. Now you can output these masks that it's identified to a file, but this won't be Hashcat ready. What it is ready for, however, is to be fed into Maskgen, which is the next tool. So if you generate some stats from Statsgen, you can give it to Maskgen, and you can tell Maskgen certain parameters about how you're going to analyze this, and then use its output in future attacks. So Maskgen will assume by default you've got a cracking speed of 1 gigahash a second, or 1 billion. You can edit this, so if you know your rig cracks at 500 million or 20 gigahashes a second, whatever it might be, you can give it a raw numeric value for the number of hashes per second. You can assign some runtime, so if you know you're only going to be running Hashcat maybe for an hour or a day, you can give it the number of seconds, so a day would be 86,400 seconds, and it will give it a target runtime. And by using Maskgen, you can identify, based on your predetermined number of guesses per second and via a time frame that you might have, how much coverage you're going to get of the masks you found in that file, so you can then apply that to future attacks. How does Maskgen identify and prioritize what's best for you? Well, it has 3 methods, but the default method is opt-index, and it says this when it's running. So by default, you'll see here it says sorting masks by their opt-index, and this is both a combination of the runtime and the complexity, and Maskgen will then try and prioritize that in the order it feels is best for you. A good example of that in situ is from this example shown here, where we can see quite low down near the bottom, we have a mask here that's lowercase letters here. That's 8 lowercase letters, and then we have another mask here just below it, which is a mixture. Now the frequency of cracks, you can see this second mask down here only cracked 1,830 passwords, so it's only relevant, it only applies to a little over 1,800 passwords, and would take 17 seconds to exhaust that mask based on the cracks per second you give it. However, the mask above it, although it takes over half an hour, it would apply and would therefore crack over 200,000 passwords. So Maskgen's determined that even though you'd have to wait half an hour longer, you get much better results by giving yourself that half an hour waiting time to crack this. Now you can change this, and we'll see how that affects your stats in the next slide, on the example we've got, of course. If we take our pot file containing masks, we're cracking at 9.8 billion guesses a second here, so 9.8 gigahashes a second, and we're going to run this for 3,600 seconds. So we're going to run this for an hour. You can see that guessing this many guesses a second for an hour would only give you 77% mask coverage of all the masks that you fed it in your pot file. It would generate 2,500 masks, and as close to an hour as Maskgen could get, it would crack 77% of the passwords. Now that's by default, by opt-index. That's generally the best one to go for. It does also support complexity and occurrence, or frequency. If we were to run the same thing for an hour, but we want Maskgen to sort on complexity, you can see here that for again around about an hour's time, it's going to generate over twice the number of masks, but it's only going to get us 53% coverage. So targeting complexity in order of complexity is not the most efficient way to go. Similarly, if we look at occurrence, again, target runtime of 1 hour, we can see it's only generated 8 masks, only giving us 31% coverage, and for reasons unbeknown to me, it can't even get it down to an hour. So we've gone wildly out there. Maskgen just can't really process this one. Needless to say, unless you've got extremely explicit requirements, opt-indexed default method of prioritization is generally the way to go for. Also with Maskgen, diminishing returns are real. You want to make sure you're getting kind of the best bang for your buck when you're running these, and you're not waiting unnecessarily for really disproportionate gains. We can look at here in this example again, taking our pot file of masks that we've given it. If we are running again at the same speed, to get 100% coverage of all of these masks, you'd be running for probably well over a year. If we run for an hour, we'll get 77% coverage. If we run for a day, 86,400 seconds, we will get 87% coverage. So by going from an hour to a day, we're getting 10% extra coverage of our masks. But going from a day to 31 days, we're only jumping from 87 to 93%. So it's almost certainly not going to be worth your while waiting an entire month just to gain an extra few percent. Well, depending on how determined some of you might be. So you can use this to identify how far you want to go based on the returns you get and the coverage you feel. And then you can, of course, apply these masks to future attacks. Got a token slide here for Jeremy Gosney, who mentioned to me that he had a couple of these files that he made, programs that he made to help order pot files. Now, this is not the most efficient way, in his words, not mine, but it can be very, very useful when you're just going to let something run. So what you do with these are you get, and we've included these on your Kali VMs, these are in your Hashcat folders. You generate an HCMask file from your pot file using dict2 HCMask here. In my example, for some reason, I've managed to compile this as a different name, but that is this binary here. So you'll give it your pot file, and then you'll see what it will do is it will go through all the planes in your pot file and generate masks that match them. What you then do after that is you take this order HCMask by keyspace binary, run that, and it will order based by keyspace, just by keyspace alone. Okay. Now, again, as I said, and Jeremy said to me, this is not the most efficient way of doing it, so we know there's no kind of warranties or caveats with this, but if you're going to let something run, you've tried some other attacks, maybe you want to give this a go, it might be interesting to see how it works, and it will order it by keyspace alone. And we have Policygen. So Policygen is for creating policy compliant masks or not, as the case may be. If you're in an environment where you've got a very interesting password policy, you can give Policygen the minimum requirements and it can generate masks based on those requirements. You're not kind of testing for anything that might not be allowed in the first place. Like Maskgen, it defaults to 1 gigahash per second cracking speed. You can again edit this and you can ask it to show you masks or show you non-compliant masks and output it as such. Here is an example where we've given Policygen a minimum length of 8, minimum lower, a minimum upper, a minimum digit and a minimum special count of 1, and we want to output this to compliant masks, for example. And it will go through and it will generate a total and a compliant number of masks, and you can see here we've got over 40,000 masks, and the results will be every possible permutation that meets this minimum requirement that you give it. Okay, and then you can use that to attack environments where you might have explicit policies defined, and this might help save a little bit of time. What we've also done on your Kali VMs is just, there's nothing special about this. This is just running Policygen a few times to concatenate together and generate a mask view that will tick all the boxes for an 8-character Windows default policy compliant mask. So three out of your 4. Technically, there's actually 5 by Microsoft documentation in terms of the character sets. There's some specific Unicode characters, but when we talk about 4, we're talking about upper, lower, decimal, and special. So what this will do is it will run through and create a file, an HCMask file that you can use with Hashcat that will go through all the possible combinations of the 3 out of 4 character sets that we typically see. And what you'll find is when you normally run by default, you'll get this many as shown in the earlier slide. But by running this, it's just a bash script that I created and put on Kali, you can reduce that number to only the ones that tick 3 out of the 4. So you won't get 4 out of 4. This assumes that the password that's been created has used only 3 out of those kind of general 4 that we see. On Kali VM that we've been testing, that I've been testing with, the one we've given you, depending on your hardware, of course, as well. You can see the types of runtime we're going to get from these, but of course, and as I've said several times throughout this training, we would never crack on a virtual machine if we were doing this properly. And if you gave it a good GPU, you can see that the key spaces to exhaust these are a lot more manageable, a lot more reasonable, and you could run this to see how many passwords drop. But that is, like I said, included for you on your Kali VMs, so feel free to have a play with that. You could even take this and then, look at feeding the output into the key space sorter that J.M. Gosney put earlier. But again, just have some fun with it. The last one is RuleGen. So RuleGen creates rules to match passwords. If you give RuleGen a password, for example, in this here, password 123, RuleGen will go through and generate rules that will crack said password. And as you can see here, we've got a few different permutations that can be used to generate password 123. You've got some more options with this that you can use to show you, suboptimal rules. Not quite sure why you'd really want to do that. And there are some ways you can sort of use this to get some interesting things out of it. I've included a blog here for further reading, but an example in situ is shown here. So if we have a dictionary that's just called testdict.txt, we can see running RuleGen over it, it's identified the top 10 rules, so 2.86% of these passwords could be cracked with this rule. So over large data sets, you could see how it might be nice to use to generate some rules that across an average might be quite hard hitting and might perform quite well. It also performs something called stemming, which is identifying the base word from a mangled password. Okay, so that's quite a nice thing too. As you can see here, it's taken this list of clear text passwords that we've got and it's tried to identify what the base words are. So as you can see here, we've got Facebook, we've got August, which are base words in some of these more mangled and complex passwords. So from a statistical analysis, it's quite nice to see how base words are being chosen before they're mangled or augmented by users to try and make them make them a little bit more secure. So that leads us on to the last exercise of the training, attack planning. So we're not actually going to be cracking any passwords in this last one. This is a kind of like a scenario that we've kind of set up to use Pack to generate some interesting statistics from that. You have a GPU, a fictitious GPU, that is cracking NTLM hashes at 40 gigahashes a second. You've just finished an assessment, you've managed to dump Active Directory and you've amassed a pot file, okay? You've extracted all the planes from your pot file and stored them in a file called rocku.txt, which may or may not be a well-known dictionary, but for this, in this scenario, we're going to use that as your pot file. Run some tests and generate some masks against your pot file on the 8-character passwords you've found, and we want to look for a few things. We want to look for what percentage of passwords comprised a lower alpha num format. We're going to try and find out how long it would take to get 100% mask coverage, and what was the highest performing mask and how many times did it occur. So let's grab Kali back for the final time. Let's CD into Pack, and we can see in here we have our files, Maskgen, Policygen, RuleGen and Statsgen. We also have this Windows pass policy one that I just quickly created if you wanted to generate Windows compliant policies to then run yourself. So let's take the first one and we're going to run Statsgen. We're going to run Statsgen over our pot file called rocku.txt. We're going to set a minimum and maximum length of 8, and we're going to output masks to rocku.masks. Now, rocku is as you know, quite a large dictionary, I mean pot file. So it might take a little bit of time just to go through this. It's going to analyse the passwords, and it's going to save the masks for us. And if we don't, of course, indicate -o rockq.masks, it won't save this. And again, depending on the size of your pot file, this could take quite a long time. So we're going to let this run, and hopefully it won't take too much longer. I don't seem to remember it taking more than a minute, and it should generate some stats for us that are going to look very similar to the ones shown here back in Statsgen. Although these numbers are going to be slightly different, of course. We're going to have some bigger numbers shown in the exercise. There we go. Right. So here we go. Analysing 20% of the passwords. Okay, now why has it done 20% of the passwords? It's because we've defined parameters of length. So only 20% of the passwords inside this are of length 8. It's excluded the rest. Okay, we can see here lower alpha num 47%. So the first question we had was what percentage of passwords comprised a lower alpha num format? Okay, and we have that here, lower alpha num 47%. Okay, this many passwords from our pot file dictionary of the lower alpha num format. The next one was how long will it take us to get mask coverage? Okay, so for this one we are going to run Maskgen. Okay, minimum length of 8, maximum length of 8. We can tell it we are cracking at 40 gigahashes a second here, and we're going to give it the mask file that we've just created from Statsgen. So we're going to feed that into Maskgen. You can see it's taken in our hashing rate. It's generated 11,625 masks using its default opt index prioritization. And to get us coverage, it's going to give us a time here of 5 hours 56 minutes. Okay. So that's our next question. It will take us 5 hours and 56 minutes to get 100% mask coverage based on a 40 gigahash attack speed on 8 character passwords. Okay, the last one, I'm going to rerun the same command, but this time I'm going to run it with outputting. So we didn't have that before, and you can see just how many masks it's gone through here. Absolutely loads of masks, and their runtimes. You'll see the runtimes here are instant or just a few number of seconds for many of them, because not a lot of these masks are absolutely huge and will take a long time to go through. But wow, this really is a lot here. Okay, what we'll then do, because that's clearly too many, I'm just going to run this with more at the end so we can see. And at the very, very top of that absolutely huge list, based on 40 gigahashes a second here, opt index, we can see that we had an 8 $D, so 8 decimals, 8 numbers, and that occurred 428,296 times. Okay, so that's the last part here. What was the highest performing mask? How many times did it occur? That's our 8 decimal mask here. Okay, so with that exercise, there are our answers. We've provided you the syntax here. That is, of course, included on your Kali VMs as well in the hidden .answers folder inside the Kali home directory. So please do refer to these. You've of course got these videos to look at as well. But that wraps things up. If this is interested you or excited you, or if you are looking to get some testing done on password resiliency in your organisation, we at In.security do offer an Active Directory password audit, which we can help you identify your credential-based weaknesses in your organisation, identify privileged accounts, privileged groups at risk inside your company, identify reuse, and a number of other things. So please do check us out if you are interested in conducting this type of assessment. As far as all the things we've covered on this training is concerned, there are a few resources here which are fantastic. Hashcrack version 3 by NetMux, which I alluded to earlier, available on Amazon. You've got the Operator Handbook, also by NetMux, and actually the last one's NetMux also, One-Time Grid, which might be a different way of choosing passwords. Highly recommend you go and check these out. Of course, shout outs to all of the team at Hashcat and NetMux as well, for all the great work that they've done and continue to do, for the references and for the help they've both not provided me, just me, but the community also. Long may it continue. If you do buy Hashcrack version 3, you will see reference to the 10 crack commandments. So as seasoned password crackers, you need to always bear this in mind. The most important one, though, allowing us to do all of this, is number 7. We shall understand that what we're doing is actually basic human psychology and behaviour. Passwords, like cybersecurity, are not a technical problem, they are a people problem. And it's our predictability that makes us vulnerable. But with that, thank you very, very much for staying with us for this training. Really hope you've enjoyed it. You can reach me Twitter, Discord, wherever as Stealthploy online. Do keep an eye on our upcoming training events. We do run Hacking Enterprises, Defending Enterprises, our free cybersecurity awareness, and more on the horizon to come if you're interested in more formal training. And we do have on our website a password cracking CTF that I released a few years ago now. At the time, we released it with a cryptocurrency prize that was swiped in just a matter of hours, but the CTF is still there. So if you want to have a bit of fun with that, download that and see if you can crack all of the hashes. Thank you very much from In.security. Really hope you've enjoyed this. Take care and happy cracking.